This is the 8th lecture and we are going to have our problem set 2, problem session 2 on the same topic, that is network analysis in the time and frequency domain, basically time, and we will start with problem 511. I will first read out the problem and then solve it. The problem 511 says an RC differentiator circuit is shown in the figure. You have an E of t, this is the input, a capacitor C and a resistance R. This voltage is V0t. Find the requirements for the RC time constant such that the output voltage V0t, what we require is V0t should be approximately the derivative of the input voltage det dt. This circuit, as you know, acts as the differentiator for a certain condition on the time constant CR. This is what you are required to find out in this problem. Now, this problem can be solved in either the time domain or the frequency domain, and as you will see, the frequency domain solution is more instructive, more revealing here. Let us first work it out in the time domain. In the time domain, you see the differential equation is that the current through the capacitor is the same as the current through the resistor, and the current through the capacitor is C ddt of the voltage across this, which is E minus V0. Therefore, E minus V0, this is the current through the capacitor, and this should be equal to the current through the resistor, and therefore, this would be equal to V0 by R. And you see, you understand this? One line differential equation. So, V0 equal to RC ddt of E minus V0. What we want is that it should be equal to well, proportional to or equal to some constant k multiplied by dE dt. We want the output to be equal to or proportional to the differential coefficient of the input, and therefore, the only disturbing feature here is V0. This is V0. If we can make V0 much less than E, then obviously this would be approximately equal to RC dE dt. The condition therefore is that the output voltage should be much smaller compared to the input voltage, and that can be ensured by making small r, by making the resistance R as small as possible. Therefore, this approximation would be valid when R tends to 0, all right, or the product CR tends to 0. All right, that is the condition. Now, this is not as revealing as the frequency domain approach. In the frequency domain approach, we simply write V0 of S divided by E of S is simply equal to R, it is a potential division, R divided by R plus 1 over SC, and this is equal to SCR divided by SCR plus 1, and it would be approximately equal to SCR, a transfer function which is proportional to S corresponds to differentiation. As you know, Laplace of d dt means multiplication by S, and therefore, this will be approximately equal to SCR, provided you can ignore this SCR in the denominator as compared to 1, all right, which means that if you work in the frequency domain, omega CR should be much less compared to 1. In other words, CR should be much less compared to 1 by omega. This is the condition. This condition is more revealing in the frequency domain approach rather than the time domain approach. The time constant CR should be much less compared to 1 by the reciprocal of twice pi times the frequency in hertz. Another way of saying this is that this would be a good differentiator for frequencies omega which are much less compared to 1 by CR. Okay? These are two ways of utilizing saying the same result. The product CR should be much less compared to 1 by omega, only then it will act as a differentiator. Now you can ask me, our input is not necessarily sinusoidal, right, but any waveform, as you know, can be expressed in terms of sinusoids. A summation, a combination of sinusoids, either discrete ones or a continuous one, as in the case of a Fourier transform, all right. And therefore, this condition is a much stronger condition than the one that we derive from the time domain, and in that sense time domain and frequency domain are complementary to each other. Some information is revealed quite easily in the frequency domain, some information is revealed quite easily in the time domain, and you must not lose sight of one or the other. And this is why I am totally opposed to blind working. An engineer cannot afford to work blindly or mechanically. Whether it is an algorithm proved in the United States, it does not matter. You must not lose sight of what is going on in the whole game.
Excuse me, sir.
Yes.
So in this question we have said V naught t is approximately the derivative of the input voltage.
That is correct.
And what we have found is that the V naught t is approximately proportional to the derivative of input voltage.
Yeah, that proportionality constant we can always adjust. You see, it is the time, it is the relationship with time that is important. Multiplication by a constant is of no concern. You can always change the multiplication by a constant.
But sir, as we have derived that RC is very small, and so V naught is equal to RC dET by dt.
So the output voltage will also be very small.
Yes, sir.
That is correct. It will be very small, and in all probability we shall have to add an op amp after this to get a sizable output voltage. Okay. Any other question? We skip one and we work out the next one. 513. 513 says, find the free response for IT. Find the free response for current IT in the figure shown, and the figure is this. There is a source there is a source. This problem would be very interesting, and I want you to follow this carefully. It is a demonstration of how physical insight can lead to an illuminating solution. 2 ohms and 1 Henry. This is the circuit. Now the question is, you are required to find out the free response. What is a free response? That is complementary function. Complementary function of the differential equation. So you are required to find the free response, actually the form of the free response, that is what is wanted. For this source under A, it is a voltage, it is a current source, and part B, it is a voltage source. Okay. The question is, given this circuit, the source is not specified to start with, the source is connected across this circuit. You are required to find out the form of the free response when the source is a current source, when the source is a voltage source, and you shall see that the two free responses are quite different from each other. One is a second order, the other is a first order. To solve this circuit, let us work, we have to work in the time domain. Okay. We are required to find out the free response, so we must put the right hand side equal to 0 and then find out the form of the response. Now let this voltage be equal to Vt, and let us first consider that the source is a current source. Source is IGT, a current source. Then obviously let us say this is IGT, we have the capacitor 1/5 farad, we have the resistance 2 ohms and the inductor 1 Henry. This is V. Obviously IGT let us say that this current, oh, free response for what? The current I, the current I, this is the current that we have to solve for. Free response for I of t, the current, all right. Okay. This is the current I. Now you can obviously see that I g of t is the current through the capacitor plus I. What is the current through the capacitor? C dV dt. So it is 1/5 dV dt plus I. Agreed? Now what I want is free response for I, so I must eliminate V. Now look at what is V. V is twice I, they drop in this, plus L di dt, so it is plus di dt. Agreed? And therefore my differential equation becomes Igt equals to 1/5 of dV dt, so 2/5 of I substitute for V, plus 1/5 of d2I dt2, or this would be di dt, thank you, this would be di dt, plus plus
L is 1.
which is 1? L is 1. Yeah, L is 1, that is why I did not write. Oh, I am sorry. No, it is okay. You are trying to confuse me? L is 1. Now this equation is okay. What I have to do now is to find a free response, which means that I put I sub gt equal to 0, and therefore.
So was there any constant Ig minus something, then we have to put that whole term is equal to 0?
That is right. The driving term is equal to 0 in absence of a drive. In absence of a drive means that if the drive was a current source, then it should be opened. If it is a voltage source, it should be shorted. Okay. So my differential equation is, if I take care of if I multiply both sides by 5, I get d2I, let us say free response is governed by the differential equation d2I dt2 plus 2 di dt plus 5 I equal to 0. This is the differential equation governing the free response, and you see the characteristic equation, put I equal to e to the st and see that the characteristic equation is s squared plus 2s plus 5 equal to 0. So the natural frequencies, which are the roots of the characteristic equation, they are given by, there are two roots, minus 2 plus minus square root of 4 minus 20 divided by 2, quadratic equation, which is equal to minus 1 plus minus j 2. Is that okay? Right. So the free response would be of the form A1 e to the power this multiplied by t plus A2 e to the power minus 1 minus j2 multiplied by t, which if you do a bit of algebra you can write free response it would be of the form some constant a multiplied by e to the power minus t, then sine of 2t plus theta, some theta. So this will be the form of the free response. It would be a damped sinusoid. All right. I am omitting all those steps. As soon as I find out the two roots satisfying the two natural frequencies, I can write A1 e to the power, let us say natural frequencies are S1t plus A2 e to the power S2t. Then I combine these two terms to put it in this form.
Can we directly use this formula?
You can, yeah.
Excuse me, sir. So if there is already some current due to some initial conditions, do we use that or include that also in the free response or not?
If there is, yes, of course. If there is some initial condition, but that will not, the initial conditions will determine these constants A and theta.
So, but you just said
Suppose
it,
there is initially a current, some form of a current in the inductor.
Okay, let me Let me explain this. You see, as far as the characteristic equation is concerned, it is independent of initial conditions. The characteristic equation is independent of initial conditions. You see, what you have to do is minus S I of 0 minus, this you have to transfer to the right hand side and put the right hand side equal to 0. So, you find the characteristic equation by de-energizing the circuit even if it had initial energy, and find the form of the free response A e to the minus t sin 2t plus theta. Then if you want to solve this completely, then what you do is you bring in the driving sources, find out the particular integral, all right, add the particular integral to the complementary function and evaluate the constants from the initial conditions. We have solved this kind of a circuit earlier. Okay. Is the point clear? What this question wants was only the form of the free response. Now, why does it want the form of the free response for two sources will now be obvious when you put this as a voltage source.
Because you don't have the initial condition here, you cannot solve that.
No, we cannot solve this. We are not also given the form of the driving function. So, we cannot solve it completely. We just require the form. Okay. Now, if it is a voltage source, suppose I have a V sub GT, then we have a capacitor of value 1/5 farad. I am working out part B. Then we have a 2 ohms and 1 Henry, and this is the current I. You see, the differential equation now is VGT equals to twice I plus di dt. Okay. This is the differential equation. The capacitor is ineffective, it does not affect the differential or the free response of this circuit. Why not? Because this is a voltage generator. Any element, okay, one way is to look at is natural response is found by short circuiting a voltage source, which short circuits 1/5 farad. The other way to look at it is that any element connected across a voltage source cannot affect its voltage. By definition, a voltage source is one which maintains its terminal voltage constant irrespective of the current drawn by it. So, irrespective of I, the voltage across 1/5 farad remains constant, and therefore 1/5 farad capacitor is ineffective in determining the free response of the circuit when the source is a voltage source. Similarly, in the previous case, if we had an element, a resistance or something in series with the current source, it would not have affected the free response. Is that clear? So, the free response here is obtained by putting this equal to 0, and you can easily see that the characteristic equation is S plus 2 equal to 0, and therefore, the free response would be of the form A e to the minus 2t, that is all. You see that when it is a voltage source, the circuit is first order. When it is a current source, the circuit is second order. When it is a voltage source, it is a simple exponential. When it is a current source, it is an exponential multiplied by a sine, and therefore, it is a decaying sinusoid. They are quite different. The free response of a circuit depends very crucially on the generator, and this is the point that was brought out by this particular example. Any question? We skip the next and go to 515.
Then 514 that I
5 foot.
complete response.
Pardon me?
514.
514 is a question asking for complete response.
Complete response.
Yeah. We take 515. 515 says, let me read the question. For the circuit shown, let us draw the circuit E of t, then you have a switch S which is closed at t equal to 0, and then you have a resistance and an inductance L. The current in this circuit is I of t. The question says the switch closes at t equal to 0, solve for I of t when the initial conditions are 0. Solve for I of t when the initial conditions are 0 and the voltage source E of t is equal to sine of omega t plus theta. Okay. We have worked out such examples, so we know the solution. Second part, so I will not work out this part. I think we can write it down. I of t would be equal to, the free response would be an exponential e to the minus r t by L, that is small t divided by the time constant. So, it would be of the form k e to the minus r t by L, this is the solution to the first part, plus the steady state response. Steady state response would be 1 by square root of r squared plus omega squared L squared, then sine of omega t plus theta minus tan inverse omega L divided by r. Wonderful. This part you can do yourself, okay, and it should be obvious. You should be able to write this solution immediately by looking at this circuit. Okay.
Write it directly.
No, it says specifically solve for I of t when the initial conditions are 0 and the voltage source is this, and therefore you will have to find the complementary function and the particular integral.
So won't while solving the force response we can take that the response will be of the form a sin omega t plus phi and then find a and phi, which is the same thing.
So long as you reach God, the path is not important. The path should be logical. In reaching God, of course, many a times the path is not logical.
So the logic is only that the response of sin omega t is of the form
Would be of the form of a sine. Yeah, that's it. That's correct. Provided the circuit is linear. In a nonlinear, this doesn't happen. Okay. Now the second part says what should be theta in terms of r, c and omega so that the coefficient of the free response term is 0. What should be theta in terms of r, c and omega such that k, the coefficient of the free response term, is 0.
It should be L. So it's C.
Pardon me?
So it's C. R, C and omega. It should be L. R, L.
Oh, r, l and omega. Okay, thank you. What we want is theta in terms of these constants so that k becomes equal to 0. Now, you notice that if the initial condition is 0, when the initial condition is 0, so I of 0 is 0, that means k would be equal to minus this quantity with t equal to 0, and isn't it obvious that k would be equal to 0 if theta equals to tan inverse omega L divided by r. Is this obvious? Yes, of course it is obvious. Put t equal to 0 here and put I of t equal to 0, then k equal to minus this quantity sine of this is 0 theta minus this, and it can be equal to 0 if theta is equal to tan inverse omega L by r. However, the solution is not unique. If theta is tan inverse omega L by r plus any multiple of pi, then also the solution is valid. But this is the primary solution, that is the lowest value of theta. Agreed? Okay, so I did not work it out in further details. 515. We skip one, go to 517. Let me read the question. For the circuit shown, let us draw the circuit. It is a 1/4 ohm resistance, then a 1 farad capacitor, and then a 1/3 Henry inductor, and this voltage is V of t. The current is I of t, and the current is given as I of t equal to 4 e to the minus 2t ut. You are required to find out Vt. Obviously, the simplest thing to do is to apply the transform technique. In the transform domain, 1 second. Is that the question 517? Yeah. In the transform domain, you see, if I take the, now I will skip a couple of steps. I can write the differential equation and then I can write I of t equal to small v divided by 1/4 plus 1 dv dt, then plus
Integral of
pardon me, integral of 0 minus to t and so on and so forth.
Initial conditions are 0.
It is not given,
So we will assume it.
we will assume. If it is not given, whatever is convenient we will assume, alright. But if you do Laplace transform, then you need not worry about it. Okay. So if let us do Laplace transform. Obviously I of s would be 4 divided by s plus 2. Is that okay? The transform of the input current. This current is the sum of the 3 currents, and obviously the current through the resistor would be 4 times V. Through the capacitor it would be S times V, agreed, and through the inductor it would be capital V divided by 1/3 S, so 3 V by S. Alright, you have to fill in these steps, but I think these are pretty obvious, so I am skipping those. And now if I collect the terms in capital V, then I get capital V equal to 4 divided by S plus 2 divided by 4 plus S plus 3 by S, which I can write as 4S divided by S plus 2, then multiplied by S squared plus 4S plus 3, and you see fortunately this can be this has real roots, so S plus 1, S plus 2, S plus 3. And now you can do partial fraction and invert term by term. Am I if you permit me to skip those steps, the final solution is given by my solution. I do not guarantee that my solutions are correct, alright, you must check. This is what I got, 6 e to the minus 3t, of course multiplied by ut. Okay. This I got directly from the transform domain and writing the equations directly. The last two problems, where we skip 518, we go to 519, the last two problems would prove to be a bit involved, so I will take a little more time for this. Is there any question on the previous one, 517? We go to 519. 519 says, and let me read the 519 gives a circuit. Okay, the circuit is 100 volt. The switch is thrown in at t equal to 0, and then you have 10 ohms, 1 Henry, 10 ohms, 1 Henry and 10 ohms. This is the circuit. The switch is closed at t equal to 0. Find I1t and I2t for 0 minus to infinity and assume 0 initial energy. Okay. So, the usual thing that we do is we write the loop equations, the mesh equations to be particular, and I get 100 ut equal to 10 and 10, 20, 20 I1. Is it okay? No, let me write in that form, 10 I1 plus di1 dt plus 10 I1 minus I2. Is that okay? Yes. All right. The second mesh Okay. Second mesh gives me 0 equal to di2 dt plus 10 I2 plus 10 I2 minus I1. Now you take the transform, Laplace transform of these two equations, and you get 100 by S equals to 20 plus S times I1. You know where this 20 comes from? 10 I1 and 10 I1. 20 and S I1 comes from di1 dt minus 10 I2, and the other equation is 0 equal to minus 10 I1 plus 20 plus S I2. Now you have a choice. You can go to the time domain. You can find the natural frequencies, write down the corresponding equations, and then make your life miserable by finding I1 0 plus and I2 0 plus. You have to find them out. Pardon me?
So one the characteristic equation we can write here.
I can write the equations.
Characteristic equation that 20 plus S minus 10 and.
That's right. That is what I am saying. After writing the characteristic equation, you solve for the roots. Then you can write the equations directly for I1t and I2t and find out K1, K2, K3, K4, whatever the constants are, from the initial conditions, which will be I1 0 plus and I2 0 plus. Alright. Whereas if you solve in the frequency domain itself, then you get simply this equation 20 plus S minus 10 minus 10 20 plus S. This matrix multiplied by the vector I1 I2 is equal to the vector 100 by S0, and you can solve for I1 and I2. I did that, and the solutions the solution for I1 is given by 100 by S0 minus 10 20 plus S, the determinant of this divided by the usual thing, determinant of 20 plus S minus 10 20 plus S. The simplification gives me, I omit a couple of steps, I have them here, but because of time I omit this, and I get 100 S plus 20 divided by S times S plus 10 S plus 30. Fortunately the roots are real. Well, there is nothing fortunate about it. If the roots are not real, if they are complex, then you know how to write a to the minus alpha t sine of omega t plus theta. Okay, you don't have to write the form of the a1 e to the power something, a2, you can write the form directly. Okay. So you have to expand this in partial fraction, evaluate the constants, and then find the current. If I omit those steps, if you permit me, my solution becomes 20 by 3 minus 5 e to the minus 10 t minus 5 by 3 e to the minus 30 t times ut. This is my solution.
In the case of I1, how come that minus 10 and 20 plus S in the determinant?
Oh, I1 is the same matrix with the first column replaced by, you don't know this, solving simultaneously? First column replaced by the right hand side. That is why 100 by S0. If I find I2, then this will go to the second column and the first column will remain as it is. Okay. This is the solution of simultaneous equations. Yes.
For this expression of I1 t at t is equal to 0, we are getting a constant, sir.
You are getting a 0.
How come this 20 by 3?
5 by 3 is 15 by, I beg your pardon, 5 is 15 by 3 and this is 5 by 3. This is one thing, very interesting point raised by him. You see, I1 of 0 is 0, inductor current initially de-energized, and therefore at t equal to 0 this must be equal to 0. It's obviously 0. 20 by 3, this is 5 by 3 and this is 15 by 3. 15 plus 5 is 20 and 20 minus 20 is exactly 0. It has to be. This is a check. What about the infinity? Infinite time value. 20. Does it check? 100 by how much was it? 100 by 5 is not 20 by 3. 100 by 15 is 20 by 3. Exactly. So these are the checks. Now the last problem is 521. 521. Let's see, where do I have? Yeah, okay. 521 says that there is a current source. I will simply indicate how to solve the problem, okay, and then leave the rest to you. I will also give the final my solution, just to convince you that I did spend time on solving the problem and getting the answer. Okay, there is a 2 ampere current source across which there is a source, there is a switch, and this switch is opened at t equal to 0. Opened at t equal to 0. That means at t equal to 0 minus the source was short circuited. All right. Then you have a 3 ohm and a 1 Henry. 1 Henry with a dot here and a 6 ohm, and this voltage is V2. For this circuit, for the transformer circuit shown, the switch S opens at t equal to 0. Find the voltage V2t for t between 0 and infinity. Assume, this is important, assume 0 initial energy, okay, which means 0 initial energy means that this current I1 of 0 minus is equal to 0, I2 of 0 minus is equal to 0. If this condition were not given, this is what I want to discuss. If this condition was not given, suppose this sentence was not there, then what would have been I1 of 0 minus? 1 ampere. Isn't that right? Because at 0 minus everything is steady, this acts as a short circuit, this is also a short circuit. No current will flow through 3 ohms. And half of this must flow here, half of this must flow here. But it says that the inductor has been so constrained that its initial energy is 0. So what it means is that there must have been a switch here which was open at t equal to 0 minus, at t equal to 0 plus 0 it is closed. Is that clear? It makes a hell of a lot of difference whether that sentence is there or not. Agreed? Okay. Now your requirement is to find I2. The mutual inductance is given as 1 Henry. What does this mean? It means m squared is equal to L1 L2, that is, it's a perfect transformer. And if it is a perfect transformer, then you know you will have to, if you work in the time domain, you will have to find out I1 0 plus and I2 0 plus. All right. On the other hand, if you work in the frequency domain, you don't bother about this. But what do you think will be the order of the circuit? Would it be, what order do you expect? I think we have done this, that if L1 L2 is equal to m squared, then it becomes a first order circuit. Okay. So if one asks you without calculating anything, can you write the form of the I1t and I2t? Obviously it will be of the form k1 plus k2 e to the power minus some constant, let us say alpha t. Agreed? Because at infinity there would be a current. Infinity, the current would be, what will be the current through the 1 Henry? 2 ampere, right. Therefore k1 is 2, k2 you have to find out from I1 of 0 plus, 0 plus, 0 minus is 0, okay. And I2t, obviously at infinity when the flux has stabilized, there is no change of flux, the current I2 shall be equal to 0, and therefore it would be simply of the form k3 e to the minus. Now what will be the time constant here? Would it be the same as alpha? or different? It is a first order circuit. It has only one natural frequency and therefore it has to be alpha t. No question. It is a first order circuit. The equation, if you find the characteristic equation, is a first order equation. So whether it is this current or this current or this voltage or this voltage, all of them will have the same time constant.
Transients should die at the same time.
Transients will die at the same rate. Okay, same rate. All right. Now, the other point about this circuit is that this is a current generator, and we have always written for a transformer a loop equation. But that is not a problem, because this can be converted into its Thevenin equivalent, that is 2 ut in series with a 3 ohm, and that is what I prefer. Instead of writing the current equation, I write a loop equation. There is nothing sacred about loop equation or node equation. You can write either, they are equally convenient. Well, I did it by making it into a Thevenin equivalent. Is the point clear? Now, the total procedure, if you go through the final solution, I think I will leave the rest of the working to you. The final solution is I1t. Now, what did you want to find out? V2. V2t is equal to 4 e to the minus 2t ut. This is the solution. You see, the time constant obviously here is half, and it is not obvious from the circuit. Isn't that clear? It is not obvious which resistance and which inductance. There are 3 inductances, 1 Henry, 1 Henry, 1 Henry, which are equivalent to 2, because the coefficient of coupling is 1. And these 2 inductances and 6 ohms and 3 ohms combine in such a manner, there is no easy way of observing and finding the time constant. You have to go through the maze. You have to write the characteristic equation and then solve for the natural frequency. That will give you this coefficient alpha. Alpha happens to be 2 here, but don't trust me completely. Sometimes I make mistakes intentionally to be pointed out later. If you cannot point out, I will have the last laugh. More tomorrow.